My name is Christophe de Bruyne, and I will be guiding you through this R2RML tutorial. I assume that you have an idea what R2RML is about based on prior lectures, and this video will be dedicated to a very simple example using data provided by an open data website taken from dublin.ie, and it contains data about weather stations in Ireland. Now, what can you find in that data set? Well, you find records about weather stations, their name, a URI leading to a page where you can find the weather readings of that station. It also contains the name of the authority or agency responsible for that weather station, and then some geospatial coordinates, latitude and longitude. And in this tutorial, we will be using a couple of ontologies and vocabularies to represent and add additional meaning to that data. But what I wanted to demonstrate and emphasize is the use of GeoSparkle. Why? Well, in GeoSparkle, there's this explicit distinction between a feature and a geometry. A feature would be something that has a place in space, such as a weather station or an airport or a country and whatnot. And those things in space have a representation that is called the geometry, and that can be a point, a polygon, a line, etc. So in a way, we need to separate the data set that we have here into two entities. Part of this data will be used to represent the feature, and parts of this data will be used to represent the geometry, and both of them will then be linked with a predicate called geo has geometry from the GeoSparkle vocabulary. Now, this tutorial is based on a more elaborate R2RML tutorial that I've developed, which you can find on GitHub, and the R2RML processor that we will avail of in this tutorial can be found here, and you can also find a pre-compiled and packaged version that you can just download and use immediately. So let's start. Here we have a editor. I use Visual Studio Code, but you can use whatever editor you want. I just use this because it allows me to put several files in different panes so that you have an idea what's going on. So what can you see here? Well, on the left-hand side, I have my R2RML processor as an executable jar file together with its dependencies, and I have a couple of files open. So first of all, the R2RML processor that we use requires a configuration file where you point to the CSV files that you want to transform into RDF, and these will then internally be turned into relational tables, and the names of these tables will be based on the name of the file. We also point to the path of our mapping file, the R2RML mapping file, and we also provide the path of the output file that needs to be generated. And as you can see, I am going to generate turtle files. Then we have our output file, which I created, but it's blank, so that you can see on the right-hand side the triples that will be generated via command line commands in the terminal below. And finally, we have our data set, weatherstations.csv, which you can find here in CSV format. Don't mind those weird characters. This is an E with a fada, which is not really well represented here in this editor. And then we have our mapping file. In that mapping file, you can already see a couple of namespaces declared. We have the namespace for R2RML. We have the namespace for RDFS, which we will be using. We have also the namespace for XSD, which will provide us the data types of some of the values that we are going to represent. Then I have included two vocabularies. One is GeoSparkle. The GeoSparkle vocabulary I have attached to the namespace Geo, but I've also availed of the basic Geo vocabulary, which has a different namespace, and I have attached it to, for the sake of brevity, to Geo2. So there's a distinction between Geo and Geo2, but we will be using those two vocabularies in this exercise. Finally, there is a fake ontology that I will be using with this namespace, www.example.org/ont and fragment. And this will only be used for demonstration purposes whenever I want to create extra predicates in the tutorial. So the next step is to start creating R2RML mapping. Let's start by creating a triples map for weather stations. So a triples map consists of a logical table, which is either a table or a view name, exactly one subject map, which provides the directives for generating the subjects in an RDF triple. A subject map can have 0 or more R2RML class statements, which will indicate the types of these subjects and will also result in triples. And then a triples map has 0 or more predicate object maps, which are responsible for generating the predicates and objects of these subjects while generating RDF. Now, in this lecture or tutorial, rather, we will not be covering graph names yet for generating RDF datasets. Those are covered in the more elaborate R2RML tutorial, which you can find on GitHub. Now, okay, let's start with generating a triples map for weather stations. So we will be using Turtle for that. So we provide a relative URI for this. This is just something I'd like to do, and I state this is an R triples map, and I will end the description of this particular resource. As I said, you need a logical table. So you need a logical table which tells the R2RML processor where to look for when you pull data from the table or query to generate the RDF in the turn maps. So we have a logical table, and we are going to use the table name, which is weather stations. Yeah, and that should be it. Now, in this particular, in the R2RML processor that we will be using in this tutorial, when you use CSV files, the names of the files will be used to create tables, and they will all be in upper case. So you can see weather stations is in lowercase, but they will be made available as a table in uppercase. Okay, that's not sufficient. We now need to create a subject map. And a subject map consists of something that will generate either the URIs for the resources or something that generates the blank node identifiers to keep internally track of which blank nodes are different from the others. In this particular case, we will be creating URIs based on some values of the CSV file. So to this end, we will use a template, and that template will be used to generate the following URI, example.org/ws, and I will be using the name column from the CSV file. Now, obviously, if you were to put these URIs in the browser, they will likely 404 unless you have set up your server to service content based on these URIs. But for this tutorial, that will do. Now, we will also state that these things, those subjects, will be of the type geo feature. And so for every URI that this subject map can generate, it will also generate a statement RDF type geo feature. Now, let's test the mapping. So this should already generate some triples. So we will run our R2RML engine in the command line java space -jar space and then R2RML.jar, and then we provide the file, the configuration file, tutorial config. And if all goes well, yep, happy days, you can see on the right hand side that we've generated for each row in our CSV file a statement that those things are an instance of feature. Now, just to demonstrate that you can provide multiple class statements, you can do it as such. We will be stating that they're instances of weather station in our fictitious ontology. So FCC weather station, voila. And that should generate 3 additional triples, and you can see that this weather station this thing is an instance of a feature and a weather station. Now, obviously, we can shorten this a little bit by stating that this subject map has the following classes, and that should work as well. Voila, and nothing changes here because it's the same. Okay, now let's start with the object maps. So I think the easiest way to start is to provide the name as an RDFS label. Each weather station has a name, so let's create a mapping for that. So we have then our very first predicate object map. Predicate object map. And a predicate object map consists of at least one predicate map and at least one object map. In this particular case, we know that the label is always the same. The predicate doesn't depend on values in the table, so we can use a constant. So we have the constant predicate, and that will be RDFS label. And now we will be using a object map, which will generate the objects in our triples. So we have an object map, and that object map will be using a column because we will be pulling the values of that column in from the table into the generated RDF. So we have a RR column, and the column that we will be using is name. Fantastic. So if I haven't made any typos, this should work. Generates, I made a typo. Triples do not terminated by a dot, so let's quickly check where a dot is missing. Name, label. Up. Line 23. Oh, I forgot a semicolon there, pardon me. And now it should work. Great. So you can see that each resource, each instance of a feature now has an RDFS label with that particular value. Now we know that these labels are also in English, so I will now demonstrate how you can provide two RDFS label statements, one for the default label and one for the same value, but then with the English language tag. How can you go about doing this? Well, we copy paste the object map. We know it's for the same predicate object map. We're generating a different value for the same predicate here. We align this, and we will now be generating values pulled from the name column, but we will add a language tag, RR language English. Now, if we just run the mapping, we will see that now each weather station has two labels, one without a language tag, which is the default label, and one with a language tag. And you can see this is English. Great. Now, what else can we transform into RDF? Let's start with the latitude and longitude of those weather stations. And we will first represent them with the basic Geo Vocabulary, because they provide two simple predicates, latitude and longitude, which are attached to the things that have those immediately. So there's no intermediate geometry object for that particular vocabulary. So we create a predicate object map, and I tend to copy paste. I'm fairly lazy, so I will copy paste, and I know that I will be generating a predicate and one object. The predicate here is Geo2, and I will first generate the latitude. And the latitude comes from the lat column, which you can find here. This one. And the longitude is the last column, but that we will cover later on in a little while. Now, if we were to run this, we will see that it does generate triples, but they're literals, they're strings. They're not really a number, and that's not what we want. We know that these values are doubles. So we need to provide a data type. And typically those data types come from the XSD namespace, and they provide a data type for double. Now, if all goes well, we will now see that those literals are tagged with a data type, and those literals have to be interpreted as a double, and that's what we wanted to achieve. We will now do the same thing for the longitude, which is pretty straightforward. You just have to replace the predicate long and change the value of the column here. And now we provide for each weather station both a latitude and a longitude. Great. Now, in the data, we can also see that they provide a URI or URL to a page containing the weather readings. We will now be using that. We will create a statement that says, well, information of that weather station can also be found there, and we will be using the predicate RDFS see also, which allows one to relate a resource to another resource, providing more information in our mapping. Okay, again, a new predicate object map. And in that predicate object map, I will be using RDFS see also, and I will be using the column weather reading. And I know that these contain URIs. So let's run this. It generates triples, but unfortunately, the URIs are represented as literals, and I wanted to create a resource. Now in R2RML, the statements column, so the predicates column, constant, and template are assumed to be generating by default something depending on whether it's a predicate map, object map, graph map, or a subject map. Now in a subject map, a subject must always be a resource, blank node, or a URI. So it assumes that whenever you use a template, you're creating a URI. Similarly, whenever you use a template, it assumes that you try to create a URI, not something else. When you use RR column, however, RR column in a subject map assumes that you're generating a URI. But if you're using RR column in a object map, well, it assumes that you're generating a value, not a URI. But if you know that this column contains a URI and you want to generate a resource identified by that URI, you need to tell the mapping engine. And you state, well, this thing generates term types of the type IRI. So we have to state that this generates things, term type of the term type RRRI. And now the mapping engine knows, okay, we have to parse this as a URI, and if that works, well, we will generate a resource. We will be running the mapping engine, and now you can see that the predicate C also points to objects that are resources. There are no more quotes around it. They're now RDF resources. And that's what we want to achieve. Now, for the last thing I want to demonstrate here is in a predicate object map, you can also have multiple predicates. So let's assume that in our dummy ontology, we also had a predicate to relate weather stations with their weather readings. So I add another predicate, FCC, and that would, for instance, be called with weather reading. Now it will generate for each object and subject 2 triples with different predicates. We will run that. And indeed, we have, for instance, Dublin Airport, we have that URI used in the triple with predicate C also, and that same URI is used in the triple with the predicate with weather reading from our fake ontology. We have now pretty much covered everything we want to describe about weather stations, except for the geometries. Before we can relate weather stations with their geometries, however, we first need to create a mapping for geometries. Let's now create a triples map for geometries, which is, again, pretty straightforward. You create a triples map, geometries. Well, it doesn't really matter. Later on, we just have to be careful that we use the same URIs, and we state that this is a triples map. Now, that triples map needs a logical table, and it's going to use the same logical table, so we can copy paste that one. Now, indeed, there's a bit of duplication. We could have created a resource for the logical table that is shared between these two, but for the sake of this tutorial, we will be keeping things rather simple. Now, in this triples map, we will be using the columns longitude and latitude, but because we're using the same table, we will actually load all the data or use all the data for that triples map. But we will later on see how we can tackle that problem by only using these columns in a SQL query. But first, we need a subject map. We create a subject map, And that subject map, instead of generating a URI for these resources, let's assume we don't want to generate resources with URI, we want to generate a blank node. Now, in R2RML, if you provide a template, it will assume that you're trying to generate a URI, unless you provide a directive that states, no, we're creating blank nodes, so you have to use these values to keep track of internal identifiers. But let me exemplify that. So I do not care about URIs for geometries. I just want to provide internal identifiers for the blank nodes. So we create an RR template, and in that template, I use the longitude and the latitude. Doesn't really matter what the strings look like as long as they're unique for this purpose. Now, if I run the mapping, it will say, well, it doesn't work. There's something wrong. These are not URIs. Indeed, we didn't state that the subjects generated by this triples map has to be a blank node. So we provide the directive RR turn type RR blank node. And now it will work. However, you can see 0 triples have been generated. Why is that? Well, we didn't provide any class directives or any other predicate object maps that could generate triples. So let's fix that. We will state that these things are instances of geometry. And now we will generate 3 triples, 3 blank nodes, 1 for each geometry. And this is what we want. Something I want to demonstrate is the values that you generate for blank nodes have to be unique for each separate resource. Now, if you by accident provide the same value, then the mapping engine will consider that you're making descriptions of the same thing. I will demonstrate that. Let's assume that I don't use variables and I just provide a constant, full bar. Now, each record in the weather station's logical table will generate the same value in the subject map, and hence the mapping engine will think that you're describing the same thing over and over again, and will just merge all the triples in for that particular resource. So I will execute the engine. For those 3 records, full bar is the value for the blank node, and indeed it results in only 1 blank node being generated for the whole data set, and that's not what we want. So make sure that whenever you use blank nodes, you're careful with providing unique identifiers for your blank nodes. Great. Now, what do we need to attach to the predicate, geometries? Well, we need to create a predicate object map that will provide us information about the point using WKT and using the GeoSparkle as WKT predicates. So I will copy paste a predicate object map from before, and I only need 1 predicate, and I won't be using a column. So the predicate will be geo as WKT. Now, the point uses 2 values from 2 columns from our dataset. So we cannot avail of column. We need to avail of a template. But remember, whenever you use a template, it will assume that you're generating a URI. So if you're using a template in an object map, you need to create a value, you need to state that. We will later see how. So we need to create an RR template, and that template is as follows. We have a point, and that point consists of the longitude and the latitude, and this will fail. Why? Well, you're using a template, and it will say, well, that's not a very valid URI. Indeed, it's not a valid URI. You need to say that this is not a URI, this is a value. So RR term type, RR literal. We need to generate a literal. And now literals are created. We will see that each geometry has a literal. However, we're not done. This is just a plain literal, simple string. We need to state that those literals are of the data type Geo WKT literal. So we need to provide a directive stating that it has a data type, and that data type is Geo WKT literal. Now, here's a bit of redundancy. We told the R2RML engine that it should generate literals here. But we also told the R2RML engine, for these objects, you need to tag them as being of the data type WKT literal. But only literals can be typed with a data type. So this one is not necessary anymore. So you can remove that one because only data types, only literals can have a data type. So R2RML is smart enough to infer that whenever you type something with a data type, well, the values created by a template must be a literal, and that will be resolved. Great. Now we have typed our WKT points with the data type GeoSparkle WKT literal. Great. I promised you to say something about the logical table. Notice that we only use longitude and latitude, so we can actually avail of SQL query, but then you have to write a query. Select long lat from weather stations. And hopefully I didn't type any typos, but now it will fire this query to the database and only use these two columns to generate all these triples. Voila. Now, the order of the triples are arbitrary, so don't be surprised if they appear in a different order. Order has no importance in RDF. This is the same RDF file that has been generated by the R2RML engine. Now, we have RDF statements for our features, which are our weather stations. We have RDF statements for our geometries, but they're not connected yet. So we will now ensure that these two are related by means of a special predicate object map. Let's connect the features with their geometries. Whenever you need to combine two R2RML triples maps, you have to be careful of the direction of your predicate. You can see that in GeoSparkle, the domain of the predicate has geometry is are features, and the range are geometries. So they go from features to geometries. And with that in mind, you then know that the predicate object map to relate features with geometries has to be declared in the triples map for features. So in our triples map for features, we will create a predicate object map that will use the predicate has geometry, but in order to generate the object, it will refer to the triples map of geometries. So let's do that. Weather stations with their geometry. First things first, let's make the exercise a little bit more realistic. Both triple maps are using the same data. Hence, we can easily join the logical tables on these two columns, longitude and latitude, and that's assuming that these are unique for each record. But let's assume that this is a different logical table and we have some sort of foreign key. Now in this exercise, that could be name. So rather than availing of a natural join, we will be using name as the join columns in our predicate object map. So I have added name as a additional column in this particular SQL query for that logical table. Now let's create the predicate object map. Again, I can be lazy. I will copy paste. I'm now in the weather station triples map, and I will create a new predicate object map. And that predicate object map is going to create triples with the predicate geosparkle has geometry. Now, I'm not going to use columns, I'm not going to use templates, I'm not going to use constants. I need to refer to another triples map, or the same one. You can have self-referencing triples map, but in this case that's not necessary. Now, how do we do that? Well, first of all, a bit of vocabulary. Whenever you create a relationship with another triples map, the triples map where you do it from is called a child, and you refer to parents. So whenever you join, you need to state which columns of the child triple map correspond to which columns in the parent triple map. So we now need to point to our parent triple map. So we state RR parent triple map, and we have to point to this one, geometries. Great. We do not want to do, for this exercise, a natural join. We will create an explicit join condition. And this tells us how the two tables should be combined by stating which values for which columns have to be the same. So we have a join condition. And a join condition consists of RR child name. So the name column in this logical table must match the name column of the parent triples map. Should be caps. If you have multiple columns that you need to join, you create multiple join conditions. But that's not necessary here. You only need to join on one column. So now we state that this triples map is related to that triples map to generate predicates with triples with the predicate has geometry, and the value will be the URIs generated with this subject map. Let's run the engine, and hopefully I haven't made any typos. It seems to be just fine. So now we should see that in each weather station, indeed, we have a geometry, which is a blank node that is of the instance geometry with a particular WKT. So they're now interlinked. In Turtle, it tries to aim for a format that is as terse as possible. That's why the blank nodes are now declared inline. So this was the tutorial, a simple tutorial on R2RML to generate RDF from a CSV file. And I encourage you to have a look at the tutorial on GitHub which is a little bit more elaborate and also introduces named graphs in the same exercise.